Swayam Prabha. Digital India. Educated India.
Welcome. So we are doing shear locking here. Now in the shear locking, basically we have studied in the last lecture that selective reduced integration and other stuff, but here in this lecture I consider a slightly advanced topic, which is incompatible elements. So where by which we can also reduce the shear locking. So now this shear locking stuff we can avoid by considering the incompatible element. Now so first of all, what is incompatible element we will discuss, and then Q6 and QM6, the two specific element which is basically popularly known as the incompatible element or non-conforming element. We will discuss that. But before we start, let us see what was the problem of the bending problem, okay, that original bending problem that we are discussing. So original bending problem, that means if I have a simple domain, and if I now consider a pure bending, let us say something like this. So this is my pure bending stuff. So what we have observed is that this in pure bending, so this is my, let us say, xi eta coordinate, because I am considering the local element. So this is the moment. So now this is MB. So now here theta is essentially theta B. So this is my theta B. Now in this bending problem, what we have observed is that lower order elements, specifically 4-noded quadrilateral, will behave something like this. So that we have observed that it will behave like this. So this is the 4-node after applying the moment. Now so the reason why it is behaving like this is because it is generating spurious shear strength. So that we have observed. Now if I consider this exact bending solution, so if I now consider, because we have seen that in case of exact bending solution, that is only epsilon xx is there and epsilon yy is new. So epsilon xx is non-zero. So epsilon yy, which is new epsilon xx, because your sigma y must be 0. So now, and gamma xy, that is has to be 0. So if I use this means conditions and then find out what is my displacements for this element, then we can see that my displacement is xi eta u bar. So what is u bar? U bar is essentially, if I consider the middle of the element is this, then from here to here, this distance is my u bar. So that means the nodal deformation. So nodal displace or x displacement is this. So this is my u bar and this is my u bar. So we discussed this in the previous classes. Now u is something like this from the exact bending solution. But what is v? V is actually, if I look carefully, to represent this curvature, this quadratic nature of this curvature, the v displacement is 1 minus xi square a u bar by 2b plus, so this is essentially, initially it was 2b by 2a. So if I draw the this thing, this is my element, that is 2a by 2b. So this is my original undeformed configuration. Now apply a pure bending moment, which is mb. So here it is mb. Now if I compute the displacement, then the displacement looks like this. This is 1 minus, this is new because of the Poisson's effect, 1 minus eta square bu bar 2a. So essentially this curvy nature, which is not present in the Q4 element, because if you remembered in the Q4 element, then this displacement I can just simply write u equals to xi eta u bar and v is 0. This is for Q4 element. Now this is for exact bending, pure bending condition. Now this will results in 0 shear strain, and naturally epsilon xx is the derivative of del u del x, and so other things. So this solution is coming from here. So now if you look carefully, that this curvy nature of this pure bending is basically due to these functions, that is 1 minus xi square and 1 minus eta square. Now this 1 minus xi square and 1 minus eta square essentially is not present in the Q4 element, because if you see the Q4 element, the shape functions for Q4 element phi I, which is I am writing in xi eta coordinate, that is 1 by 4 1 minus plus xi and 1 minus plus eta. Now where I is 1, 2, 3, 4. So now so naturally this element cannot simulate or cannot approximate this pure bending curvature. So now naturally the one way is to use reduced integration to avoid these things that we have studied, and another way is obviously go for higher order element. For instance, this will not be present if I use 8 noded element or 9 noded element, 2D element itself. So if I use, for instance, this 2-dimensional quadratic element like these elements with a mid node, so naturally this mid node will give me the quadratic variation, so it can represent this. But if still I want to use the lower order element, and then I want to modify that element in such a manner that it can represent this, one way is to consider incompatible modes. So we have studied what are the modes of Q4 element, already we have studied those things. So if I consider incompatible modes, now let us see what are the incompatible modes. So for instance, if I add these two functions in my shape function in the 4-noded quadrilateral itself or 4-noded element itself, for instance, let us consider this element 4-noded. So this is 1, 2, 3, 4. Now my shape functions are like this. So u is essentially I am writing u in xi eta coordinate only. So that means 1 by 4, or I can write it in a summation manner, because these are already we have studied. So I equals to 1 to 4, and then phi I ui, right? So this is my approximation, standard approximation. Now with this standard approximation, if I add these shape functions or these additional functions with the approximation, so what will happen? Let us assume that this is essentially like this, that is I is my 4 to 5 to 6. So I equals to 1 to 4. Now this is I equals to 5 to 6. Phi I and some di. Di's are basically the constants. So now see this element, similarly for the v, if I write v as xi eta is summation of I equals to 1 to 4 phi I vi plus summation of I equals to 5 to, okay, let us say this is not di, let us say this is alpha I. So I will use d somewhere. So phi I beta I. Okay. So now what is the phi 5 and phi 6? So phi 5 xi eta is essentially 1 minus xi square, and phi 6 xi eta is 1 minus eta square. So now if you look carefully that we have only 4 nodes, but we are adding more unknowns. So alpha I and beta i's are unknown. So there are 4 additional unknowns we are considering. Now this will create an incompatibility in the system. Why? Because if you look carefully that what these, because these displacement, these shape functions are not corresponding to any particular node, because we have already used 4 shape functions for each of these 4 nodes in the Q4 element. But these additional shape functions phi 6, phi 5 and phi 6, they are actually not connected to any node. So essentially not connected to any degrees of freedom. But additionally there are 2 constants alpha I and beta I. If we consider, then this will create incompatibility. Why? Because let us see why it may so happen. Suppose I want to so let us say I have alpha, if I just extend these expressions, so that is my u. So the first term, let us keep simple like this. So phi I ui plus your if I expand this, so 1 minus xi square alpha 1 or alpha 5 plus 1 minus eta square alpha 6. Similarly, v is summation of I equals to 1 to 4 phi I vi plus 1 minus xi square beta 5 and 1 minus eta square beta 6. If I use this, now suppose for if I try to simulate only or if I consider this part of the approximation, then how it will look like, right? So suppose this is my this thing element. So now this means this will vary along xi axis. So xi, if it is so this is my eta and this is my xi. So now if xi equals to 0, it will be some value, that is alpha 5, and if xi equals to 1, that is plus minus 1, then it will be 0. So xi varies along this line. So it will be something like this. Suppose this is something like this. So now if I use xi equal, so similarly at this line is the xi variation. So naturally here also we will have this, but eta is different. So this is not, this is independent of eta. So this will look like its shape. So and what is this alpha 5? Now when xi equals to 0, that means at this point, so at this point this is my essentially alpha 5. So and this is my alpha 5. So you see in case of 1 minus eta square, this may also so happen that it will be something like this, it will be something like this. So this will be something like alpha 6 and this is alpha 6. So that means the mid point, even though at that point there is no node, this alpha 1, alpha 5 and alpha 6, similarly beta 5 and beta 6 represents V displacement. So this actually creates incompatibility, because consider a neighboring element. If this mode or this, so these modes are called incompatible modes. Incompatible modes. So now if suppose this mode is activated in this element, but the neighboring element, this mode need not to be activated. So it can activate a different mode altogether. So that will create a gap or overlap in the system. For instance, if I just draw a simple two element system, then you can understand this clearly. So this basically two neighboring element. Now suppose if it is activated, some modes are activated here, right, and some modes are activated here, right. So some modes are activated here, some modes are activated here. So similarly, if I have this similar kind of activation, then what will happen? This will have overlap or gap. So this is actually creating a gap or incompatibility. So this will actually creating an incompatibility. So this can happen for single element also. For instance, means not necessarily altogether all modes need to be activated. For instance, in this case, so here if I consider two element, if this mode is activated, this mode is activated, but for this element this mode is activated. So now what will happen, actually there will be a gap here, right, and there will be overlap with the adjacent element. So this is actually incompatible. This is not allowed in the variational solution. So sometimes that's why it is called variational crime. So I will come to that in a later moment. Now, so we understand what is incompatibility means. But if you use standard finite element, standard Q4 element, this incompatibility at the boundary you will not observe, because if you see that in this standard 4-noded element, that at the boundary this is a linear polynomial. So if I plot this linear polynomial, it is like this. Now in the adjacent boundary you will have similar polynomial which is coming to this side. So that means there is a continuity in the boundary. So this is actually violated here. So this incompatibility violation is associated with these incompatible modes in this structure. Now this incompatible, that's why it is called incompatible element. So incompatible modes. So this, if I do this, remember one thing, that we are not additionally introducing any nodes. So now how to approach this? But one advantage of this, that if by introducing these modes we can easily represent the correct bending solution. So which is this solution? So this we can easily represent this correct bending solution with these modes. So that's why incompatible elements are useful in finite element solution. So first first it has come in this in this first reference. The first reference, Wilson actually proposed this element. So what he proposed, let us discuss. So this is Wilson et al. Element. So what he proposed is basically the same thing, that U is approximated and V is approximated like this. So then what is my stiffness matrix? The stiffness matrix is our simple integral B transpose CB. So now here in d omega. So this is my in a single element, let us consider a single element. So this is my stiffness matrix. Now in this stiffness matrix, since there are four additional constants in an element, so naturally my strain displacement matrix will be now 3 cross 12 matrix. So if I write my strain displacement matrix, that is B, that will come like this, that is B1, B2, B3, B4. These are my standard coming from this phi I, which is I equals to 1 to 4. And then there will be additionally B5 and B6 will be there. So this so these are submatrices obviously. So these are each 3 by 2 matrix. So now this actually creates my B matrix is 3 cross 12 matrix. Now if this B is my 3 cross 12 matrix, the procedure is very same. The way, instead of 4 shape functions, I will use 6 shape functions. The procedure is overall exactly same with the Q4 element, just only extended number of shape functions. So this is my 3 cross 12 matrix. So naturally its transpose will be 12 cross 3. So if I write 12 cross 3, that is, this is my 12 cross 3 matrix, and this is again my 3 cross 3 matrix, and this is my 3 cross 12 matrix. So finally this stiffness matrix will be 12 cross 12 matrix. Now look, if I have a 12 cross 12 matrix, but we don't have associated node for that. So what is the possible way is to condense out these additional degrees of freedom. So that can be very easily done. So for instance, if I write this stiffness matrix now in this manner, now if I can write my stiffness matrix like this. So what is D and delta, I will explain. So delta is essentially your simple this U1, B1, U2, V2, U3, V3 and U4, V4. Those 8 degrees of freedom that is associated with Q4 element. And D is essentially your alpha 1, beta 1, alpha 2, beta 2. So these are my additional constants that is due to the incompatible modes. So now I can substructure my stiffness matrix like this. Now look, because of these additional modes, there will be no forces, because since there is no node, so naturally this equation I can the elemental equilibrium equation for this element I can write like this, that is K delta delta, K delta D and K D delta, K D D into your delta D equals to your Fe, that is elemental force vector due to traction or body force or any other time. And so remember one thing, that body force, when you compute body force or surface traction, we don't use these incompatible modes, because that will actually violate the continuity condition, because if I use the incompatible modes, that total volume will not be conserved. So that's why while calculating the body force and the surface traction, we essentially use the standard Q4 shape functions for computing this. So only for calculating stiffness matrix, these incompatible modes is considered. Now if I use this, then I can easily remove these degrees of freedom or these constants from the overall stiffness matrix. So basically from the second equation, if I now see that KD delta into delta plus KDD into D, so these are all submatrices and these are vectors, subvectors. So this into D must be equals to 0. So naturally if I want to find out D, then D is my minus KDD inverse K D delta into delta. So KDD is actually 4 cross 4. So KD delta is essentially 4 cross 8. So this is 8 cross 1. So basically this is 4 cross 1 vector. So now from the first equation, if I now compute from the first equation, then what will happen, that K delta delta, so this is standard your B matrix, that is this is K delta delta is essentially your standard Q4 B matrix, that is omega E B transpose CB. So this is my standard B matrix, which is here B is actually 8 cross 3, then this is 3 cross 3 and then 3 cross 8. So this is standard B matrix. So K delta delta into delta plus your K delta D, which is this, and multiplied by D equals to Fe, right? So now this equation I can easily now substitute the previous result, that is K delta delta into delta plus K delta D, right? Now D is my minus, so I will change the sign here. So this is now minus, so here D I will substitute, which is KDD inverse KD delta into delta equals to Fe. Now naturally I can take delta common, so K delta delta minus K delta D is Fe. Now here you see here there is no D, the constants, the alpha beta constants are not there, so that's condensed out. So this is my now stiffness matrix. So this is modified stiffness matrix over the element. So this modified stiffness matrix multiplied by the delta is your Fe. So this is for the incompatible thing. Now what is Ke? Ke bar. So Ke bar is essentially this K delta delta, which is standard 8 cross 8 matrix, and then minus K delta D, which is your 8 cross 4 matrix, and then KDD inverse, which is 4 cross 4 matrix, 4 cross 4 matrix, and then K D delta, that is your 4 cross 8 matrix. So this is my modified stiffness. Now if you use this, then you can actually represent the bending modes correctly. Even with the one thickness element, you can actually correctly represent the correctly simulate the bending problem. Now there is a problem in this element. So it was soon discovered that there is a problem with this element. The problem is actually it doesn't pass the standard patch test. The patch test we discussed in the previous class briefly, that is the completeness criteria. So completeness, how if I apply a linear polynomial to Q4, then the displacement boundary, then in a standard patch I should recover the exact results at the internal nodes. So that's how. So it passes patch test only if there is a rectangular element. So what later that modification came through this Taylor's second reference. In this second reference, a modification came, and which with that modification, this can be applied to general quadrilateral element. So that modification is very simple. I will discuss it because what Taylor argued is that if I give a linear displacement field at the nodes, so then these pure incompatible modes should not be activated. So that's the completeness condition. So if you remember the completeness condition of Q4 element, that is your suppose U, the completeness condition. So U is actually summation of say phi I. So completeness condition for Q4. So phi I, your let us say consider some variable, that is Ui. So the boundary variable. Now this phi I, this boundaries, if I apply the boundary boundary nodes, if I apply some displacement which is linear polynomial, according to linear polynomial, that is say C0 plus C1 xi plus C2 yi. So these are according to, so ui is something like this. If I apply to all boundary nodes 1, 2, 3, 4, then what will happen if I substitute this C0 plus C0, C1, C2 are constants. So C0 plus C1 xi plus C2 yi, if I just substitute this, and then I can just take this out, that is phi I, then C0. So C0 plus summation of phi I xi into C1 plus summation of phi I yi, that is your C2. Now this is, we know that is 1, and this is actually your xi. We know that is x essentially. For the isoparametric formulation, we know that x is summation of phi I xi, and similarly y is summation of phi I yi. So if I do this, then I can write this x, and this I can write this y. So basically it represents that C0 plus C1x plus C2y. That means if I apply a nodal displacement in such a manner that it represents a linear polynomial everywhere in this element. So these are functions of x and y. So u is a function of xy. So everywhere in the element this linear pattern of this displacement is prevailed. So that is called completeness condition. So what Taylor argued, that if I give a linear displacement to the incompatible elements, then naturally the incompatible modes should not be activated. So with this argument, he showed that condition that if you look from our previous incompatibility condition, that is k delta delta k d delta d and k d delta and then k dd into your delta and d, then this d must be 0 essentially. So that means from the second equation, if I write the Fe and 0, from the second equation if I write, that is k d delta into delta plus k dd into d should be 0. Now what Taylor argued is that if I apply this linear displacement field to the incompatible element, then these d modes or d coefficient should not be activated. So that means this quantity must be 0. So naturally if d is 0, then this quantity must be 0. So naturally what is the condition for this completeness or the completeness condition for the incompatible element? So that means this must go to 0. So what is the meaning of this? So this is essentially k d delta into delta. So if I now write this in integral form, that is integral, so what is this? So this is nothing but b, say let us give some name. So let us say BA. Okay, BA transpose or BA transpose CB. I will explain each B here, and this is d omega multiplied by delta. Right. Now what I did here is essentially I decomposed the B for incompatible element is let us say B bar here. Okay, decompose this B as B1. We have we remember this B's. So B1, B2, B3, B4 and then B5 and B6. So naturally this is my B bar, which is standard B, and then this is I am calling BA. So naturally this is my this thing. So this is standard 8 cross 8 B bar, and this is your 8 cross 4 sorry, this is 3 cross 8 B, 3 cross 8 B, and this is my 3 cross 4B. So that's why this B becomes 3 cross 12B. So this is BA, and which is coming from the stiffness matrix manipulation or the substructuring of the stiffness matrix. So naturally this BA contains B5 and B6. Now that means if I just now if I put this thing equals to 0, that then what it means? That means that integral BA transpose C B bar into delta, let us say delta I take inside, then d omega must be equals to 0. So that means integral BA transpose C B bar delta, that is B is standard B matrix, which is 3 cross 8 matrix here. So now this is nothing but your stress matrix, right? So this is stress vector. So I can write it like this: BA transpose equals to 0. Now stress is actually your arbitrary. So naturally this quantity B integral BA d omega must go to 0. So that means if I take out this stress, so since stress is arbitrary, it can happen in any simulation, the arbitrary stress. So BA transpose d omega sigma should be equals to 0. So this quantity, to make it 0, sigma cannot be non-zero, so then it is a trivial solution. So this quantity must go to 0. So this is the condition that Taylor proposed. Now what is this integral BA transpose d omega? So now this condition means that is you have B5 and B6. So this transpose d omega is 0, must be equals to 0. So now that means individually this has to be 0. So that means integral B5 d omega must go to 0, and integral B6 d omega must go to 0. Now B5 and B6 are what? So B5 is essentially your if you write the B matrix, that is 5 comma x 0 0 5 5 comma y 5 5 comma y 5 5 comma x. So this comma means the derivative. That means 5 5 comma x means del 5 5 by del x. Okay. So similarly for y. So now this B5, if I now for an arbitrary quadrilateral, if I now map to a master element through this thing, then what it will look like. So let us now do it here. So if I do these things here, so integral B5 is this. So that means 5 5 comma x 0 0 5 5 comma x, that is 5 5 comma x, sorry, this is y, 5 5 comma x, this is y. So this d omega must be equals to 0. So now I will check whether it goes to 0 or not. So now I convert this thing to the master domain. So naturally my integral will be -1 to +1. So that is my this thing. So now if I B5 comma x, if you remember with the help of Jacobian we can modify. So let me write that B5 what it comes, that is del phi by del phi 5 by del xi into del xi into del x. So this is my this quantity. So then this is del phi 5 by del xi. Then see phi 5 is my 1 minus xi square, right? So only xi derivative exists. So that's why del xi by del y. Now this is again del phi 5 by del xi into del xi by del y, and this is del phi by del xi into del xi by del x. Now this is my sorry, this is again I have to write it in so this is my det j, the determinants of Jacobian, and then d xi d eta. Now what is the meaning of this? Now if I now substitute my xi's, that is -1 to +1, then integral -1 to +1, then this quantity I know d phi 5 by d xi. Phi 5 is 1 minus xi square. So this will be my 2 xi. So let me take 2 outside. So 2 xi, and d xi by dx I can get it from here, because I know d xi by dx. I think these things you have studied, d xi by dx and d xi by dy, d xi d eta by dx. So Jacobian I think we have studied, d xi by dy. This is essentially equals to your 1 by j, det of j, that is my dy by d xi d eta minus dx by d eta minus dy by d xi and dx by, so Jacobian inverse essentially, dx by d xi. So if I now with the help of this, if I substitute, then d xi by dx will be I have to compute, which I can compute, which is dy by d eta. So now I can write this as, so there will be minus, so dy by d eta, so 0 and then 0, then this will be your d phi by d xi is minus xi. So 2 I have taken outside, so d xi by dy. So naturally d xi by dy is your minus dx d eta, so minus will cancel. So naturally now it will be dx by d eta, and this will also be xi dx by d eta, and this will be my minus xi dy by d eta. So this if I now this j will cancel with here, so this is d xi d eta. Similarly that b6 integral b6, so that is integral b6 d omega becomes, I will write the final form, so that is integral eta dy by d xi 0 0 eta. So b6 is my 1 minus eta square. So this is minus 1 to plus 1, minus 1 to plus 1, so this is 2, and then this is dx by d xi. So this is minus, so minus eta dx by d xi. So the same procedure I followed. So this is eta dy by d xi. Now this is d xi d eta. Right now here if you look carefully, that what Taylor has seen, that this dy d xi is actually constant if the element is rectangular or parallelogram form. But if it is an arbitrary quadrilateral, then because of the linear interpolation, bilinear interpolation function, this dy by d xi and dx by d xi, dx by d eta and dy by d eta, this term will have linear components. So naturally we can understand this from our this thing, because x we know that is phi I into xi. So naturally phi i's are my isoparametric form, that is all 4 shape functions, 1 minus 1 by 4 1 minus xi into 1 minus eta x1 and so on. So if I take del x by or del y by del xi or del y by del eta, then the linear terms will come which is not taken as the derivative. So those terms will be for an arbitrary quadrilateral will be there. But if I use a rectangular quadrilateral, a rectangular polynomial, a rectangular kind of simple domain or a parallelogram, then these things will be constant. So you can verify that, it is very easy. So these things will be constants. So means it is easily verifiable, because if you consider a simple rectangular element, then these two nodes will not have any x variation. So that is essentially 0. So naturally this will be 0. So naturally if this if I have a simple parallelogram, so this will be, the difference between this will be constant and difference between this will be constant. So that will actually so if these quantities are constants, if these quantities are constants which is applicable for the rectangular element, then what will happen, this integral will go to 0. And why it will go to 0? Because xi, if I take the integration, then it will be xi square. So xi square, if I put this if I integrate -1 to +1, then naturally it will be 0. So what Taylor suggested that instead of doing this, what he did that instead of doing this, so he modified this equation, and he modified in this way, that let us consider or let us calculate these derivatives at the center of the element instead of the Gauss point, which is plus minus 1 by root 3. If you remember the 2 cross 2 integration rule. So instead of Gauss point, because this is Gaussian integration, right? So instead of Gauss points, which is plus minus 1 by root 3, let us calculate at the center, that is xi and eta equals to 0. So this will actually eventually nullify the linear term. So that will pop up as a constant term. So then this -1 plus 1 -1 plus 1, so this will be now, instead of doing this, then this he calculated that xi, then dy by d eta, instead of calculated at the Gauss point, so this is at xi equals to 0, eta equals to 0. Similarly for xi, look, this can be variable, right? Because the objective is to make this term constant. So xi dx d eta at xi equals to 0, eta equals to 0. Then this is also 0. So now xi dx dou x or del x, whatever you call, xi equals to 0, eta equals to 0. Then minus xi dou y by dou eta at xi equals to 0, eta equals to 0. So this is what he calculated, and naturally this will be 0 if you put the linear this thing. So that is applicable for all elements. So for rectangular element, for any arbitrarily quadrilateral, this will be simple. So what is Taylor's B5? So if I write the B5 for Taylor, that is your 2 by j. Okay, let me use some different 2 by j. So B5 is essentially 2 by j So not the integral one. Okay, so that is minus xi. So this quantity, that is if I write y comma eta, that is calculated at 0, 0 point. Now this is your 0, this is your 0, then xi x comma eta will be calculated at 0, 0. So now this is xi x comma eta calculated at 0, 0, and then this is minus xi y comma eta calculated at 0, 0. So that means that evaluated B matrix at the center of the element. So similarly B6 also 2 by j. So if I write this, that is eta y comma xi 0, 0, 0, then 0 eta x comma xi evaluated at 0, 0. So this is an ad hoc trick, obviously. So eta, so this will be minus, so x comma xi 0, 0. So this is eta y comma xi eta 0 comma 0. So you can see that this will not give the this will always give the satisfy the patch test or the completeness condition for that element. Now this modification is very much ad hoc type. Now there is several other modification came also. For instance, Adnan Ibrahim Begovic and Taylor itself proposed a different modification. So these even these days several modification, and these days are these topics are active research. So these topics are wide open till and obviously some research is going on in this area. So these incompatible elements, however, is from the basic which we have studied, that very basic incompatible element. This is very helpful in restricting or capturing the bending mode in the lower order element. Now obviously this ad hoc incompatibility actually creates variational crime, and naturally we don't so that's not variationally consistent in the procedure. So even the finite element softwares also implemented this incompatible elements. For instance, Abacus uses deformation gradient base or the deformation gradient base incompatibility, which avoids some of these things. So those are very advanced topics. So if you want to go through the so this fourth reference were a modified method of incompatible modes. So these things you can just go through to learn those things. So this completes our shear locking part. So in the next lecture onwards, we will start volumetric locking. So thank you.